Hello, maurieo on turning points in their nature. Hello, welcome. Well, today a couple of students came and asked me the question that you see just over here. Use calculus to find the coordinates of the stationary points of the function below and determine their nature. Y equals x cubed minus 6x squared plus 9x plus 1. So what I'm trying to do is I always try to lead students into first of all trying to work these things out for themselves rather than just have me show them various things. So I asked them a few questions, and it transpired that first of all they sort of weren't too aware of calculus at all in the differentiation and what stationary points were and how to determine their nature. Now, it had been some time since I've done this myself, and so I attempted to sort of show them from memory without doing too much homework myself. And well, I made a few little errors along the way, so I decided that I'd do this video here just to sort of, on the one hand, demonstrate how we might go about finding things out and sort of methodologies that we can use to become independent learners and teach ourselves, and then go along and ask the right questions. So first of all, I want to just go across to the big screen here where I've got the question set up there, but I've just got smooth draw 4 here. So first of all, I just wanted to draw this little parabola here, y equals negative x squared, like so. And what you can see on there is that this point here is the turning point. That's the turning point there, or the stationary point. Turning point. I should point out that my writing is not that flash. I have a bit of a condition that means that I don't write very well. So I used to write a lot better than this, but not anymore. I'm a wee bit shaky and a bit weak in the hands, but I'll do my best, and hopefully you can read it. So that's a turning point there. Now, as you can see, if we look at the gradient of the graph, you can see that we've got a point there, and if I just draw a tangent through there, that's that would be a positive gradient, positive. And if I just chose another point over here, that would be, and drew a line through there like that, if I could draw a line through there, that would be a negative gradient. Remember the gradient equals rise over run. Rise over run. And so gradients that increase from left to right, positive, and gradients that decrease from left to right, negative. So if we look over here, we can see that that's increasing from left to right, positive, negative. Now, if we just look at the gradient at a turning point, the gradient there equals 0. At turning points, the gradient equals 0. Okay, and that's y equals negative x squared. And that, when that's, you've got a turning point like that, that's what we call a maximum. A maximum. Okay. And if we look at the alternative one here, which is y equals x squared, this parabola here, there's the turning point there, and you can see that the gradient down that side will be positive. Oh, it's going decreasing, will be negative. And the gradient on this side here will be positive at say a point there and a point there, and through here the gradient will be negative. Now that's y equals x squared. Now the differential equation dy by dx and this one here, of course, would be a minimum, a local minimum, or a minimum, and that one a maximum. Now dy by dx is the gradient function, so it tells us the gradient of the at these points, dy by dx. If we do that, it tells us the gradient at these points. So if this here is y equals x squared, and I'll just change over to a bit of a green color here, just to put, I'll just put these as they're supposed to be grid lines. So that's 0, 0 there. So perhaps not a very good example, but anyway, if we go dy by dx of x squared, so for this one here, I'll probably put that purple. So we can go dy by dx x squared equals 2x. Okay, so if we want to, and that equals 0 when x equals 0. So if we look at any the gradients along here, if we look at the gradients where x is less than 0, all right, we'll see. So this x squared. Oh, sorry, negative x squared. That one's negative x squared, so that'll be negative 2. Okay, so that'll give us the gradient. So we're the gradient between sort of coming up to 0, the gradients on this side here of the thing there, that'll be negative 2, and these will be negative, so they'll all be positive gradients, as you can see. Positive gradient there, so that'll be positive. And then the gradients on this side, where x is positive, will be negative. Okay, so that you can see how that determines the gradient. And obviously the turning point, when this equals 0, so negative 2x would equal 0 when x equals 0. Okay, which is what we're seeing there. Now this one here, dy by dx of x squared equals 2x. And we can see in that case there that remember, that's telling us the gradient. So everything on this side from here this way, those gradients there are going to be negative x, so they're going to be negative. and you can see how that coincides with that negative one there, and everything this way, they're going to be positive gradients. So this is the differentiation. So it gives us the gradient, and then obviously the same thing, 2x 2x equals 0 when x equals 0. Okay, so that means that yeah, we can that determines, you know, the turning points. So we can look at the turning points and we can actually examine what they look like. So what we can do here now is we can look at maybe this gradient function here, perhaps what color? Oh, maybe I'll go to blue, maybe blue. Okay, so we can do this. So we can say, no, that's not good. We'll go back to red. Okay, so we can go dy by dx, in this case here, as if we differentiate this. Now, let's differentiate this. So we take 3, bring that to the front, 3x squared, okay, minus, we got 2 times 6 is 12x. So what we do is we bring this number to the front and subtract 1. So 3x to the power of 2. This one here, 2 times 6 is 12, so that's negative 12, and that's x. And then this, and this here is plus 9. Okay, so that's like there's a 1 there. 1 times 9 is 1. That's it. And that's it differentiated. The constant just disappears. Now that's there. So at a turning point, or stationary point, at a turning point, gradient equals 0. Our gradient equals 0. So we get 3x squared minus 12x plus 9 equals 0. Now, I can see that 3 goes into that, so I'm going to put a 3 in here outside this bracket, and then I'm going to put 3, and then I'm going to go x squared minus 4x, because 3 goes into 12 4 times, plus 9 plus 3, sorry, 9 plus 3 equals 0. And then I'm going to factorize this quadratic here, and I'm going to get 3 x. Now this sign here is positive, but this is negative. So that must mean that either they're both negative or both positive. In this case, they're both negative. So I'm going to go x minus 3, like that. And then I'm going to go x minus 1. So that's factorized it. That's factorized that there. Okay. And so what we can say is when that equals 0, the turning points turning points are when x minus 3 equals 0 and x equals 3 and and x minus 1 equals 0 and x equals 1. Okay, and we can also say that, okay, so there where the two turning points are. Now we know this is some sort of cubic graph. It's a cubic graph, so it's some sort of, we know that cubic graphs go something like, if we draw this in here, like we might have a cubic graph can go sort of, they can have that might be a cubic graph and this might be the turning point. So it's not the one in this case, but that's a cubic graph. They go something along that of that sort of nature. So that's sort of cubic. So we know that we're going to get two cubic graph. So we know that we're going to get something like that. So what we're going to do now is attempt to just to draw it up. Perhaps I'll use green for that. Green. So what I'm going to do is, I'll leave that there. So I'm going to put that down in there like that. That's along there like that. So we've got when x equals 3, which is maybe here, and we've got when x equals 1, which we'll put there. So if we go back to our original graph here, this here, when x equals 1, okay, y will equal 1 minus 6 plus 9 plus 1, and that'll equal 1 minus 6 is negative 5, plus 9 is 4, plus 1 is 5. Okay, so x, let's just check. So that'll be 1 minus 6 minus 5 plus 4 plus 5. So that's 1, and let's say 5 there. So that's going to go through that point. So that's going to be a bit of a turning point there. Okay. And when x equals 3, we're going to get 27. 3 cubed is 27 minus, now 3 squared is 9, 6 and 6 nines are 54, plus 27 plus 1 and that equals 5, right? So when x equals 3, we get 27. 3 cubed is 27 minus 6 nines are 54 plus 27, so that's all 0 plus 1. And that doesn't equal 5, it equals 1. So I'll just write that. Okay, that equals equals 1. Oops. Control Z undoes that. Try and get a 1 in there. Oh, having a bit of trouble here. Equals 1. So we're going to get a point here, a turning point there and there. Now there's another point that we can easily determine on the graph, and that is when x equals 0. I'm having a bit of trouble here. When x equals 0, y will equal these 0, 0, 0, 1. So when x equals 0, y will equal 1, which is also about there. So that's what's happening there. And the graph doesn't cross the... No, we don't know where... They're the turning points. We don't know what the other factors are. So there could be other things that we can find out. But one of the things that we can find out is the nature of the turning points. Okay, and that's the nature of the turning points. And we can do that over here. I'll do that nature of the turning points, or TPs. And that is done by the second derivative. And we look at the TPs, the second derivative, and that's d2y by dx squared. And in this case, so we take the derivative of, well, I'll just undo that there. D2y dx of 3 for some reason now it's going of 3 something. What's happening here? Why is it doing that? I must have pushed some sort of button here or something. Oh damn. Why is it? Can't get it to write now. Oh, here we go. Okay. Control Z, dy by dx of the, so that's going to be, what did I say, 3x squared. Oh. Let's do that. Three x squared minus 12x plus 9, so that's, well that's actually, yeah, of we differentiate that again to get the second derivative. So that's 2 3s are 6x minus 12. Okay, 6x minus 12. That's the second derivative. Okay, so that's the second derivative of the original thing, but I've just differentiated that there. Okay, so when x equals 1, d2y by dx squared equals 6 times 1 is 6, minus 12 is negative 6. So it's a negative. And that tells us that the turning point is increasing negative, or is increasing negative, and so that means, like, as it goes from left to right, it'll go into a it'll start going negative, like here. So it'll, from the turning point, it's starting to go negative, increasing negative. So that tells us that that's a minimum. Minimum when x equals 1, and when x equals 3, d2y by dx squared will equal 3 6s are 18, minus 12 will equal 6. It's positive. So that means that the function is increasing positive, or the gradient function is going positive. So that's up like that. Sorry, I've got that wrong. That there's a maximum when it's negative. I've just got a little bit bamboozled there. So that should be a maximum when it's negative. I was actually pointing to a maximum. So when x equals 1, it's negative 6, and so as you can see, it's starting to go negative. So that's increasing as negative. So that's a maximum. And here where it's positive, so it's starting to increase positive, like the gradient's going positive. So that there must be a minimum. Minimum. Okay, so it's when it's positive, it's a minimum, and when it's negative, it's a maximum. So now if we go to our graph, we can see that when x is 1, it's a maximum. So that's indicating that, oops, I didn't change the color. So that's indicating that as it's coming up here, it's a maximum, and then it's coming down here like that, and it's a minimum there like that, and then it's going to come down here like that. So that's sort of what's happening. So to get the turning points, or the answer, the TP's turning points are at 1 and 5. and that one's the one at 1 and 5 is a maximum. And then the other one's at 3 and 1. The turning point at 3 and 1, and that one's a minimum. Okay, and so the name, yeah, so that's it there, like so. It's a bit shaky, sorry about that, but that's the best I can do. Now, so let's just go and have a look at that. And what I've done here is I've set up here a graph here, a graphing function thing here, which is this one here. That's it there. And our function that we're looking at is here, and I just need to check back on that. So I'll just come back to here. X cubed minus 6x squared plus 9x plus 1. So it's getting x cubed. So we'll put that in here. X cubed, x raised to the power of 3 minus 6x to the power of 2. Let's go back again. X cubed minus 6x squared plus 9x plus 1. So then it'll be plus 9x plus 1. Now the thing is, we don't have the beauty of this in an exam situation, but we can do this here, and let's just plot this. And there it is there. Now we can see here that here's our function, and here's our maximum at 1, 5, and our minimum at 3, 1. Here like so, with the turning points, which confirms what we got, although it's drawn somewhat a bit better. And I'm sure that you'll be able to draw a bit better than I, but I think you can see. So just to recap on this, we started with the function there. Then the next thing we did was we differentiated it, and then we set that to 0, and solving that gave us the turning points, that the turning points were at x equals 3 and x equals 1. I wonder if we can just, let's drop this into here. Perhaps not. Never mind. Okay, so the turning points were at x equals 1 and x equals 3. And we know that tells us there. And then we sort of start to drawing up the graph there to get a bit of an idea of what it looked like. And then we started looking at the nature of the TPs over here. So we found out the y-intercept here. The y-intercept here. Okay, that gave us a bit of a clue that it must be doing something like that. And then we looked at the nature of the turning points over here, and so we differentiated this here to give us d2y there. So that equals let's put that there. That equals that there, differentiated with respect to x dx, if you like. So yeah, so the second differential, which is 6x minus 12. So then we look at what happens when x equals 1. 6x minus 12 is negative. Okay, so that tells us that's a maximum. And I got that a little bit ahead of myself there, but it is actually a maximum. And one way of looking at that is that look at what the function does. So at a maximum, it starts to go negative. All right, and that tells us that it's going downhill, so that must be a maximum, negative. Okay, then when x equals 3, we can see that it's starting to go uphill again because it's positive, increasing positive grade, and so that tells us that it's a minimum. You know, that these gradients are here, these ones, yeah. So that's what's happening. And so that enables us to draw the there. So in an exam situation, this is all the information you've got, your pen and your pencil and your calculator. When you're in doing some study beforehand, you have the luxury of these other technologies that, well, can help you to conform or confirm what you've done and that sort of thing there, which is what we've used there with graphsketch.com. There, and then back to here. So what we can do is just go back to here, and I've just gone through that and hopefully solved that a little bit anyway, and just shown a little bit of an answer there for that one. It's a little bit sketchy. I'm afraid my writing is a bit on the shaky side, so I hope you don't find that's not too confusing. But yeah, that's just a bit of a roundup of things there and how they go, and explaining that one there. I hope if you've got any questions, you've got the comments below that you can look at and ask me any questions, and I'll see if I can answer them for you. Oh, good. Cheers. See you.